In this video, I'm going to design and build my own electric bike using a 3D printer and some electronics. E-bikes are an awesome way to get around, but after seeing how expensive they are, I quickly changed my mind of buying one. A high-end e-bike like the Specialized model that I liked cost almost $6,000. Instead, I decided to see if I can build my own more powerful one for a fraction of the price. The first step was choosing the right base. For this project, I decided to use my Specialized mountain bike because I already had it and it was strong and lightweight, which is exactly what I need. The next important challenge was figuring out where to put the motor. On a normal e-bike, you generally have two main drive systems. The first one is called a mid-drive motor. These motors are small and efficient, but they are integrated into the pedal system, which makes them more complicated and quite expensive. Plus, you have to pedal at all times, and if you ask me, I don't really like that. However, you can get around this issue with the other option. Hub motors, on the other hand, sit directly inside a bike's wheel. This makes them simple because they are not integrated into the pedal system, but they are pretty heavy and it usually requires you to replace the whole wheel. For my design, I wanted to combine advantages of both systems, something that could be compact enough to fit a normal mountain bike while still being able to power the bike independently and not replacing the rear wheel. After that, it was time to buy the motor. When choosing a hobby-grade motor, you generally have two important values you need to look at. The first one is obviously size, which is usually represented by a 4-digit number. The first two digits represent the diameter of the motor and the second two digits represent the length of the motor. So a common motor, like a 64mm in diameter and a 74mm in length, would be called a 6474. The other value is kV, which is a little bit more complicated, but it basically tells you how many rotations per minute, or RPM, the motor spins per volt. So if you have a motor that's about 200 kV, and you power it by a 42V battery, the theoretical maximum speed should be around 8400 RPM. But here comes the problem. If we connected this motor to the bike's wheel directly, it would be going nearly the speed of sound. And for obvious reasons, we really can't do that. But this is just calculations, because in the real world, the torque from the motor wouldn't even have enough power to even move the bike. So probably it wouldn't even move at all. So we need a better way to trade speed for torque, and in engineering this solution is quite simple. By using a small gear driving a larger gear, we can reduce its output speed but increase its torque. For example, with something like a 10-to-1 reduction, the output gear will spin 10 times as slow, but with the 10 times the torque. This is possible because the small input gear spins much faster than the output gear, and that means that the torque is evenly distributed over multiple rotations. However, as I learned in this project, there are a lot of problems, and remember when I said to you that I'm using a hobby-grade drone motor? Well, these motors in general spin very fast, usually in the thousands of RPM, meaning that if we want to achieve the torque and speed that we need to slow them down a lot. And for that, we use a bigger reductions, obviously. But with bigger reductions, you have bigger gears, and on a mountain bike, you really just can't fit anything. So if we take an example from my reduction that's 15-to-1 or roughly 15-to-1, you would need probably like a 20-tooth gear driving a 300-tooth gear, and this 300-tooth gear would be so big that we couldn't fit on a bike. So to get around this issue, you generally have two options. Number one, buy a different motor that's slower, and I'm not gonna do that because I already have this one. And the second option is using multiple stages. And what I mean by that is that if we use the output gear as an input gear to the second stage, we can reduce the speed by multiplying these two stages together. So for example, if you have two stages that's 4-to-1, the output speed will be 16-to-1. The downside to this solution, however, is that every stage introduces some energy loss. And this harms the efficiency of the motor quite a bit, but I would say this is a fair compromise for its compact size. And as you can see, this is where the real challenge of designing DIY motors begin. Everything is just a compromise between size, efficiency, torque, and speed. So now that I knew what the system needed, it was time to start designing the motor itself. And this part just ended up taking so much longer than I thought. At first, I experimented with some 3D printed gears, and after hearing their beautiful sound, I decided to switch to belt drive. A belt drive is just so much more quieter, smoother, and actually more friendly to 3D print. My plan was basically to run an HTDEM 5M belt from the back wheel to the bike's frame. And this of course meant designing a custom pulley for the rear wheel. The brake disc turned out to be a perfect mounting point, although there was one small problem. I had to sacrifice my rear brake for the system, which probably isn't the smartest idea, but for testing this concept, it was definitely the easiest solution. And please do not copy this setup. Riding a bike with only one brake is pretty dangerous and I don't recommend it to anyone. The rear pulley is actually made out of two separate parts. The first part is mounted directly on the brake disc, and the second part gets screwed onto this using M3 screws. The reason I made it this way is because it allows me to easily change the gear ratio without having to print the entire pulley again. For these parts, I use Prusament PC Blend, which is honestly one of my favorite filaments. It is strong and lightweight, which makes it perfect for mechanical parts. And the white pulley is just a transparent PLA that I already had lying around. After solving the wheel side of the system, it was time to move on to the motor itself. Since I wanted this to fit on a normal mountain bike, I decided to take advantage of the existing mounting holes for the bottle. The design is actually pretty simple. It is an open motor mount and two reduction stages, one on each side, and this gets me the heat reduction ratio that the motor needs. I also made a sliding mechanism that allows me to move the motor back and forth. This is very useful for tensioning the belt, and trust me when I say that keeping the belt very well tensioned is actually really important, especially when you're using not so precise 3D printed gears. Looking back, using 3D printed pulleys is probably not the best idea. After a few rides, you can tell that the gears had seen brighter days, but getting these parts CNC machined out of aluminium would have made this project so much more expensive, and I wanted to see if the idea even worked at first. So I assembled everything together and finally mounted it on the bike. The next challenge was making the motor actually controllable. For this, I used the VESC Classic 100 volts from VESC Labs. If you don't know what a VESC is, it's basically a smart control that allows you to take control over much more than just speed, and it controls things like RPM, current, torque, and much more. And for any bike, this is extremely important. For example, a normal RC airplane like my mini Flying Wing here is much more simple. This is because the motor experiences pretty predictable loads, but on an e-bike this is a different story. Because if you're going downhill, uphill, or accelerating from zero, it all takes different amount of torque. And without the proper control, it's actually very easy to overload the motor and burn it. I actually learned this the hard way. The first controller that I bought was a cheaper Maytag VESC, and it just ended up not working at all. The funny thing is that the price difference even wasn't that big. The Maytag was around $140 and the original VESC Classic was around $220. So if I could give you one piece of advice, don't cheap out on these important electronics, because saving a little money just creates more problems later. Mounting the VESC itself to the motor was actually pretty simple. I 3D printed this mount with tray inserts and I just glued it into the motor. And the VESC just got screwed with M3 screws. One thing that I really like about this controller is this little button. I really don't know what it is, but it just makes me feel like this is an actual e-bike, so it is really cool. The final big challenge was choosing the right battery. And trust me when I say that I looked through many different options, and the one that caught my eye was actually a drill battery. And this made the whole thing just so much more convenient. You just take it out, charge it normally, and put it back in. It's super easy. The hardest part about this is making a good battery adapter. For this, I just ended up using something I found online and it ended up working perfectly. I modified it a little bit, added an XT60 connector, and that just got attached to the bike. After that, I just wired up the rest of the things and the whole thing was ready for a test ride. This was really exciting because after more than 2 months of work, I finally had it done. If there is anything that puts a smile on my face, it's testing something you've built yourself for the first time. It's such a unique feeling. So, did the hard work pay off? Yes, it did. I rode this bike literally everywhere for the next few weeks and I really love it. And for the cost, including the bike itself, this project came to be around $1,650. Compared to a high-end e-bike, this means that I saved roughly $4,350. But the price isn't certainly the only thing I'm happy with. One of the biggest advantages of my design is its weight. The whole setup, including the battery, just weighs about 3.5 kilograms, which is super lightweight for its capabilities. This bike turned out to be way more powerful than I thought it would be. Its max power on acceleration or hill climbs is around 800 watts, which is certainly not bad for a 3D printed motor. It can handle all sorts of hill climbs pretty easily, but you have to help it a little bit with pedaling, like a normal e-bike. What is really nice about it is that it doesn't have a speed limit, and this allows me to accelerate the bike without having to pedal at all, which is super fun. The fastest I ever went on this bike is around 40 km per hour. After that, the motor just stops producing any power, because the RPM of the back wheel exceeds the maximum RPM of the motor. But to be honest, I think it's a very sufficient speed for a mountain bike. Some of you might wonder about range. So far, I haven't done any data logging yet because I don't have a Bluetooth module, but we can at least try to estimate it. To calculate the overall range, you need to know your total battery capacity and your average energy consumption. With my 12 amp hour battery, we can expect roughly 240 watt hours of capacity. This basically means that the battery can output 240 watts for 1 hour or 120 watts for 2 hours and so on. In the world of commercial e-bikes, the battery this size isn't something very impressive. Standard e-bikes usually have batteries that are about 500 watt hours. But again, my setup weighs around 10 kilograms less. Energy consumption, on the other hand, is a little harder to guess without any data logging. But if we use a common value of 11 watt hours per kilometer, the math gives us an estimated range of about 21 kilometers. At first, this may not seem like a lot, but considering how compact and lightweight the system is, I would say it is a great result. The biggest problem that I have with this bike is that on hill climbs or acceleration, the belt would occasionally skip. This happens because the FDM 3D printed pulleys are just not precise enough to have a proper teeth engagement. For heavy load applications like on an e-bike, this is a really big problem, and every now and then the belt pulleys would just snap. I was able to reduce this problem by tensioning the belt more, but that only helped so far. Unfortunately, this takes extra power from the motor and it's not able to accelerate as quickly. Right now, I'm actually working on an MK4, and I hope to get rid of this issue for good. I'm gonna be using steel pulleys now, so that should do the trick. This new version is gonna be so much better, I really can't wait, but this is just for another video. Anyways, that's for this version. I learned a lot of cool things along the way, and I think that I understand a lot more about mechanical design and electromotors. My name is Adam Hayek, I want to thank you so much for watching this video, and I will catch you in the next project. Bye!